Hi guys, this is section 7.1 and this is on power functions. Here's your journal choice and it's a pretty simple journal I think you should consider doing. So go ahead and jot that down if you think this is one that interests you. Okay, what do you know about x to the n? Well, you guys should know a lot about this. This is called powering whenever you take something to some power. X to the n, the big number x here, that is the base. The little number, what do they call that? A superscript, I think. This is the exponent. And the entire expression, when it's considered together, that is actually called a power. Okay? So that's a little bit of terminology there. Base is the important one. They'll ask you what is the base of power a lot of times. And exponent, that comes up also because this tells us a lot about the graph. So those are some important words for you to know. Moving on, there's a shortcut to figuring out this. You guys know what x to the n means, okay? What does x to the n mean? Well, it means x times x times x times x times x times x. And I could do this forever. How long will I need to do this? Well, I need to do that n times. How long I multiply is determined on the exponent. This tells you how many times to multiply. How many times? It is called repeated multiplication. Okay, the textbook does a really nice job of writing this as a recursive formula. It says the first term is x. The mystery term is going to be x times the one before it. I should put t. Where's my eraser? So you take the term before it, which is n minus 1, and you multiply it by x, because each time you're going to take it times x, and that would be 4 integers, n greater than or equal to 2. Okay, so you start with x, and then each time you multiply the next term by x again. Now this is a helpful definition whenever you look at this situation. Calculate the value of 14 to the fourth without a calculator, given that 14 to the third is 2744. So what that tells us is 14 to the fourth is really, the term before it would be 14 to the third times 14 again. So we know what 14 to the third is. 14 to the third is 2744. So if I take that times 14, I will get 14 to the fourth. Now it says to do it without your calculator. Truthfully, I would have reached for my calculator, but we're going to do a little old school multiplication review. This will take you back to your elementary days. Can you guys remember who taught you how to multiply? I had Mrs. Bennett, and she taught me how to multiply. I think that's 4th grade. You guys can correct me if I'm wrong tomorrow. Okay, 4 times 4 is 16. 16 carry the 1, 17. 28, 29, 8, 9, 10. Okay, so that's the first one. Drop a 0. Everybody always forgets to do that. 4, 4, 7, 2. And looks like 6, 11, 14, 8, 38,416. If I made a mistake, I'm sure you guys will all tell me tomorrow. Oh, I could go to the calculator. What am I taking? 14 to the 4th power. 14 caret 4. Enter. Oh yeah. I think I'm a superstar. Okay, so that is a shortcut, kind of. It's a long cut, I know. But what you can do is if you know any of the bases, you can take that and then multiply by the extra 14s. It's always going to be 14 though. Okay, this is a application of power functions. And we're going to take a look. When you use an exponent, it is going to be a function because if I take 14 squared, I'm not going to get the same thing as if I take 14 to the third. You're always going to get a new value, so you're never going to get repeated. So this is a function. Its graph would pass the vertical line test. Every x value only shoots out one y value. Okay, so we're looking at y equals x to the n. Now, some people might say, there are too many variables here. The only variables we're talking about are y and x. This n will, you could put any number in here and it will still be a function. Okay, so it's kind of like a constant, but we will pick what constant it is because it will have different behavior. Okay, so probability, this is the most fun you'll have with power functions, I think. Because probability is fun because people like to gamble. I think it's just because we're naturally competitive. I am not encouraging you to gamble, but calculating the odds it's a fun thing to do. So this will be a direct application to this. This is the example of probability of repeated independent events. Things happening in a row. When should you stop? Okay, if an event has probability P, and if each occurrence is independent is important here when you're talking about probability. We are talking about like rolling a die or spinning a spinner. Those are independent events. Things like rain, that's not an independent event because if it rains today, it might not be as likely, or it might be more likely to rain tomorrow because there's a storm coming in or whatever. So only independent events, one that doesn't depend on another one. So if an event has probability P, and if each occurrence is independent of all other occurrences, then the probability that the event happens n times the row is P to the n. And I wrote not good. And if you look in the textbook, there's a really awesome graph, and I did include it on the next slide. And I want to talk to you about it because this graph was a little confusing, but once I explain it to you, I think it's going to make perfect sense. It says A equals P to the 4. P is the probability. That's what we're going to be plugging in here. And this 4 is telling me how many times in a row I'm talking about. Okay? So A is also a probability, but this is like the total probability. And we're not adding the probabilities, but here's what I'm talking about. The probability, I should say, of happening once is P. Is happening, have one N, okay. When I take it to the 4th power, it's happening 4 times in a row. So let's talk about what 1 is. Notice this graph does stop at 1 because a probability is a number between 0 and 1. I had a statistics professor who said this all the time. 0 means, if it has a probability of 0, that means not going to happen. Okay? If you have a probability of 1, that means it's a for sure thing. And you can't get better than for sure. It's either going to happen or it's not going to happen. And this is the stuff that happens in between. Okay? So if it has a probability of 1, it is going to happen. It has a spinner that doesn't have any like sectors or sections. It's all red. So what's the probability that you're going to spin red if there's only one color you could possibly spin? Well, duh. It's going to happen. It's 100%. Probability of 1. So what's the probability it's going to happen 4 times in a row? Well, this is your total probability over here. The probability that if it happens once, it's 100%. Well, if it happens 4 times, it's still 100%. Okay? Same thing with 0 and 0. If it's not going to happen, if it's that red spinner, and I said what's the probability that it's going to end up blue? Well, it's not going to happen. So what's the probability that it will happen 4 times in a row? Still not going to happen. So 0, 0, and 1, 1 are our boundaries. Now this is where it gets super exciting to me. Anyway, let's say that we're talking about flipping a coin. Okay, the probability of it getting heads is 1/2, right? 1 out of 2. Now, the probability of getting heads 4 times in a row. Okay, here's how it works. You're going to take the 1/2, that's the probability of it happening once, and then times in a row goes up here. So it's 1/2 to the 4th power. Now 1/2 is right here, 0.5. Look at this. Are you going to get it 4 times in a row? Chances are not good. Okay, for it to happen 4 times in a row, it's going to be less than a 10% chance, it looks like. And we can get the exact number here, 0.5, and I don't know if you guys can read this. This is really tiny. 0.5, oh, you can read it over here, I see, to the 4th power. 0.06, yeah, it's like a 6% chance that you can do that. And I know that some of you have done it before, but that doesn't speak to the truth of the thing, that the probability is only 6%. Okay, now, this is one that's most exciting to me. If I said that Matt Murphy was a 90% free throw shooter, okay, what are the chances that he's going to make 4 in a row? Okay, now this is really not a good example because those aren't really technically independent, especially when you're shooting in a row. You can really kind of make adjustments. So that was probably a really stupid example. So let's say I have a spinner, because that's definitely independent, and it's into 10 regions, 9 of them are red. And I said, I will give you, I'll bet you $1,000 that you can't get 4 in a row. Would you take the bet or not? 90% chance. That seems pretty good to me. I think I'd take it. Okay, so let's say 90%. 90% is right here, 4 times in a row. I thought it would be a for sure thing, but if you look, it's just over 60% chance, 0.6. Okay, it's still above a 50-50 shot, but if I asked you that same question, would you flip a coin for $1,000? I don't know that you would say yes. This 90% is misleading because when it's in a row, it really goes down quickly. If I said 8 regions were red, would you take it? That's below 50%. If you get 80% chance of spinning a spinner 4 times in a row, goes to 40% chance of that happening. Okay, I hope this chart makes sense to you. Oh, look, I didn't even notice this table was there too. It's actually 25%. This tells you the probability of it once, the probability of 4 times in a row. Look how quickly that drops. Okay, so just take in mind, anytime you make a bet for in a row, not a wise thing. Okay. If the probability event is 0.6, what is the probability that it will happen n times in a row? Well, that will be 0.6 to the nth power. Okay, simple power functions, these are things you should know. X to the first is x, so y equals x. If you put something in, you're going to get the same thing out. This is called the identity function, because whatever you put in, the same thing comes out. If I made a t-table, it would look the same in both. The graph looks like a 45-degree line. Oh, that's horrible. But it's all the same. Okay, y equals x squared is a squaring function. Y equals x squared is a cubing function. Those are the ones you need to know. All other power functions don't have special names, but we are going to look at domain and range right now. Okay, you need to get your graphing calculators out, and I want you to see some patterns here. And what I'm wanting you to look at, oh, I needed to do annotate over. I want you to look at graphs like this. So y equals x, we know what that looks like. It looks like a line, okay? Then I want you to try y equals x squared. Then y equals x to the third. Then y equals x to the fourth. Y equals x to the fifth. Okay? Let's look at some of these. This will be exciting. I'll move this over here. Okay, so let's go to control, new page. I'd like to add a, graph. Okay, let's try y equals x squared. I think everybody knows what that looks like, don't you? Looks like oh, there it is. It's lovely. Okay, y equals x squared is a parabola. Now let's try y equals x to the third. The caret key is right there. And we get some like snaky thing. Okay, y equals x to the fourth. X to the fourth. Okay, we get a narrower parabola looking thing. It's not quite a parabola. It's not actually called a parabola. I don't know if you can see this, but it's a little flatter in here. Okay, that is significant. Y equals x to the fifth. I love graphs. Okie dokie. X to the fifth. Again, looking like a snake, a little narrower, and again, a little flatter in this region. Okay, so y equals x to the sixth. Anybody want to predict what that will look like? I hope that you have a prediction that it's going to pop back up. And if you look, I'm just going to go to a new page actually because my graph is getting, well, let's just see if you can tell. Y equals x to the 6. Where's it at? Yes, orange. It's back up. Y equals x to the 7th goes back to the snake. Okay, so there are some patterns that you should have noticed. And here is a nice little chart that explains them. Some ordered pairs are always going to be there. If it's even, 0, 0, 1, 1, negative 1, 1 are going to be there. Why? Because this is a form of direct variation. Y equals k is 1, x to the n. And if you remember, 1, 1 will always be there if k is 1, because that point 1 comma k will be there. So that's why 1, 1 is there. No matter if it's odd or even, because the point 1k will always be there. Now, if it's odd, it's a little bit different because negative 1, 1 is there and negative 1, positive 1 are there. Okay, so this is going to look like this. And as odd, it's going to look like this. You might want to draw a little sketch for yourself. Domain, left to right, all real numbers. I can plug whatever I want into this, but what am I going to get out? I'm only going to get positive numbers whenever I have an even power. Think about that. When I plug it in a negative and I square it, it comes out to be positive. If I do it 3 times, oh, it's negative again. So you get all real numbers when it's odd. This is only in quadrants 1 and 2. Keep in mind the Roman numerals. If that comes up later, you do need to put Roman numerals. 1 and 3 if it is odd. There is some symmetry. We got symmetric over the y-axis. And this one has rotational symmetry. Okay? So that is really all I have for you today. And I will see you tomorrow. Oh, just kidding. So what type of symmetry does this have? X 19th. It's odd. It's going to have rotational symmetry. I've got the power. Okay, that's it. See you guys.